this webinar it aims to showcase exciting research results, inspire and motivate new research, and create a regular recurring opportunity for the AsiaGraphics community to meet and exchange ideas. So this is session 22, and we are very glad to introduce Professor Juyong Zhang from USTC of China and Shunsuke Saito from Meta. So the first talk is from Professor Juyong Zhang. Let me first introduce Professor Zhang. Professor Zhang is a professor in the School of Mathematical Science at the University of Science and Technology of China. He received his BS degree from the University of Science and Technology of China in 2006. And the PhD from Nanyang Technology University at Singapore. His research interests include computer graphics, 3D computer vision, and the numerical optimization. He serves as the associate editor for IEEE Transactions on Multimedia and IEEE Computer Graphics and Applications. So today, the talk from Professor Zhang is monocular camera-based high fidelity digital human modeling and animation. So let's welcome Professor Zhang.
Okay, thank you. Can you hear me?
Yes.
Okay. Okay. First, thanks for the kind introduction. Hello, everyone. I'm Juyong Zhang from USTC, and I'm honored to be invited to give this talk about molecular camera-based digital human modeling and animation. Okay, so recently VR, AR, and the metaverse attract a lot of attention from industry, academic, and for example, some bigger companies like Microsoft and Meta, they invested a lot of manpower and resources to do building their system, like Microsoft's Fusion 4D and Meta's Horizon Workroom system. So what these systems need to effectively and efficiently digitalize the real physical world, including the environment, the object, and especially the human, including the shape and motions. So currently, digital human has been already successfully applied to movies like the left one, the Anita Bad Engine, and the right one, the Ready Player One. And another application example is Google's Starline, which is Google's next generation 3D video chat booth. So you slide into a booth, and your image is supposed to be projected to another booth in real time, as if they are actually sitting with somebody else across a table. So in this system, they first reconstruct the digital human and transfer the reconstructed model to another side. Currently, the most popular approach is based on camera array. For example, as shown in this slide, one of the most famous example is Jason Huang's digital human. Its digital human has been used for the presentation of 2020 the GTC conference. To digitalize Jason Huang, they utilize our camera array, including around maybe around 100 cameras to capture multi-view images, and based this based on this well-constrained lighting and camera setup, it can recover a high-quality geometry shape, appearance, and lighting, and it can support further editing. But however, it still has some limitations, like require constrained capture environment and needs a complex modeling process, and the cost of this hardware and the modeling process is quite expensive. So therefore, it can only be used for top companies and research labs. So recently, some research effort is divided to this sparse camera-based digital human modeling. For example, based on this 3 or to 5 cameras, they can recover high quality geometry shapes and motions and synthesize lower value and lower motions. We can see that the cost and capture convenience has been greatly improved compared with the camera-only solution. However, this kind of capture hardware is still out of reach for the general public. So this is because it is almost impossible to do camera synchronization and calibration for ordinary users. So our target is to do this digital human modeling based on just one single camera. The reason is that we will have like this smartphone, and we can use our smartphone to easily capture a short video. So as shown in this example, we can use this smartphone capture a very short video, like maybe 20 seconds, and we design several algorithms to reconstruct its corresponding geometry shape and motions for the face, for the head, and the body. So based on this reconstruction result, we can use that for the many upstream applications. So our group has conducted some research effort toward this target. Maybe around 4 years ago, we adopted this parametric 3D face shape face models like 3D morphable model and face warehouse to do this 3D face reconstruction and tracking from just one single view image. As shown in this demo, based on this input one single view image, we can recover its corresponding smooth surface shape, and the rendered result is also quite okay for the first part. But we can see that based on this parametric model, which only contain around 100 parameters, so the strength part is that it has a fast computation speed, and meanwhile, due to its low dimension representation formulation, it has a limited representation ability. For example, it can only recover the face part without the hair and the teeth part. So therefore, it is more suited for the tracking task rather than the high fidelity reconstruction task. For the human body, we also conducted some research work about this closed body modeling from a single input image. We also achieved this target based on this constructed parametric model. So this paper is published in 2020 ECCV. As shown in this example, so this is the input image, and we can do body and clothes reconstruction simultaneously. Similarly, it has limited representation and generalization ability due to the constructed low dimension parametric model. For example, as shown in this 3 examples, the clothes has been separated as 2 parts, but the input image they just has one skirt because but it failed to recover this skirt because the parametric model doesn't have this type of clothes. Okay, this is what we did in this based on this parametric model for the head, for the face, and the human body. So our first work in this direction is this prior guided multi-view head reconstruction. So the input is with some sparse view image. What we wanted to do is to design our algorithm to reconstruct the whole head model with hairs. So actually, this is a very first work toward this. Not only the face part, but what the whole head, including the hair. So this paper is published in Transaction Multimedia, but actually this work has been finished around 2019. Okay. So the main idea of this work is include two parts, different from existing mesh-based representation, like a 3D morph model or festival house. We didn't utilize the mesh representation. We adopted this linear implicit function-based SDF, like it means that side distance function to represent the reconstructed head model. We also to guide the reconstruction process, we adopted the differentiable rendering to do this kind of self-supervised reconstruction process. So actually, in 2019, so the LORF is not published. So we at that time we use this based on this IDR. It's based on this differentiable surface rendering, not volumetric rendering. So okay. Meanwhile, we also utilize some priors like this landmark and face passing and this 2D direction of the hair part. So we use this kind of prior information to guide the reconstruction process. And the surface is represented by this kind of linear implicit function based on SDF. And we guide this reconstruction process based on this differentiable rendering pipeline. Okay, with this kind of a lower design, we can recover high fidelity reconstruction result. Okay, let me give some details. Okay, so first, because for this kind of nonlinear optimization, we need to give a good initial solution. So we utilize this parametric model. So we utilize this 3D morphic model recover from this multi-view image. We do this kind of inverse rendering and recover the identity and the expression coefficient to recover its corresponding initial surface shape. And based on this kind of loss, it's like a photometric loss and landmark and this regularization. And we also we get this semantic labels such as shown in this here, it's like the loss and the face and hair. It's like this to do this face passing. Meanwhile, we also recover the hair. So we to do this two-dimension direction detection for the hair part, and from this 2D we recover its corresponding 3D direction, and we utilize this the above mentioned three kind of priors to guide the reconstruction process. Okay, let me show one example. As shown in this example, the user can directly use this smartphone to do self-capture or ask his friend to help capture the video. During the capture process, the user keep as rigid as possible based on this captured multi-view image. So as shown in this slide, from this short video, maybe just like 10 seconds, we can reconstruct a high fidelity geometry shape and corresponding textures. Okay, we show more result. We can see that with only a short video, we can recover high quality surface shape of the head part, including the tooth and the eyes, and different from parametric models like 3D morph model or flame, which can only recover the face part. Our method can recover the whole head model, and the reconstruction accuracy is much better compared with this kind of parametric models. So the first work is only for this static head part, but it's only recover this static and cannot be animated, which limit its applications. So meanwhile, it requires that the user keep as rigid as possible during capture. So which is not convenient for some users. So therefore, we extend this the last work from static to dynamic, and it has two benefits. First, it frees the user to arbitrary expressions and motions, and thus can be easily captured. Second, the captured video contains the user's personalized expression information, and thus the recovered head model can be used for animation and retargeting. This is a pipeline. Actually, the pipeline is quite similar with the last work. So the input is a molecular video with arbitrary pose and expression and motion, and output is an animatable high-fidelity head model. As a different frame has different expressions and poses, so we first to utilize this parametric model to initialize the deformation between different frames. So because the different frame has different expression code, and then adopt this deformation field to further refine the long-range deformation. Similarly, we also adopt the facial prior, including this semantic segmentation, landmark, and parametric model to do this initialization and constrain the reconstruction result. And so the main difference from this pipeline and with the last pipeline is that because this is a dynamic video, so different frame has different surface shape. So we adopt this like a dynamic deformation field to model the non-rigid deformation. Okay, so this shows some result. So the input is okay. Let me play again. So this is the input single video. We show that we have the whole algorithm contains several component, and like this with only deformation, without segmentation, without this kind of 3D morphable or frame. We combine this together. We can say that the final result is much better. For just one component. Okay.
Excuse me, Juyong. Actually, I cannot see the video very smooth. It's a little bit break. So
okay.
Actually, I don't know the reason. So can you change Wi-Fi or something else?
Okay. Just wait 1 minute. Okay.
Okay.
Maybe change the Wi-Fi. Okay. Okay. Can you see my slides?
Yes, I can see your slides. Can you play the video again?
Yeah, I already played the video.
Actually, it's still not very smooth.
Smooth. Okay. Actually, I changed my Wi-Fi to okay. Okay.
How about we just change the method to present the the PowerPoint.
Change the PowerPoint.
Yeah, not full screen. Just use your I mean.
Oh, I see. Okay. Like this?
Yes. It's much better actually.
Okay.
So but in this mode we cannot see all the videos play simultaneously, right?
Oh, okay. So yeah, just we have two videos and just play one by one.
Okay. So how about we squeeze the sidebar and so that we can see the PowerPoint much bigger.
What do you mean? Sidebar? Which sidebar?
The sidebar on the left. So just squeeze.
Oh, okay. You mean here, like this? No. Hmm. But okay. So how about it? Sorry.
So how about you just push the button on the left bottom, just on the left of the PPT presenting button. The 喂，哎，是这样，就是你点一下下面有一个翻书的那个小按钮，PPT 上，对，然后你再放一下 video，我看一下，对，这个好像可以了，您可以切一页，再切一页，切到之前的2页，我看一下。好多了，可以放了，这样的话，您能看到备注吗？它这个 Zoom 是不是有点卡？对，它就卡到那种，它可能就很多动态的区域都已经完全卡住了。您再放一下呢？现在应该是演讲者模式，您可以切一下。对，这样这个模式没问题，但是就是怕您看不到那个备注。对，呃，所以就是这个确实或者就是就是不用播放模式，就直接就是在编辑的那个页面。对。
这样的话就是视频的话，你就一个一个点着放就行啊。但是在这里就是先把左边那个拖一下，就是让这个 PPT 啊，但这样也会看到备注哈，我们会看到备注。那您再放一下，我看一下手机的这个网行不行？因为我刚才以为是我的问题，然后我上 YouTube 那个直播看的话，YouTube 上也卡，所以我才跟您说的。
Okay, can you hear me?
Yeah.
Yeah, you can just play the video again.
Okay.
So how about you close your video, your web camera?
Oh, okay. Yeah, maybe this. Yeah. Okay, maybe can get it better.
Yeah. And
play again. Okay.
yeah, play again. So it's a little bit better, but still not very perfect, actually.
Okay. Oh, yeah. Maybe I need to change the setting. Okay. So
Okay.
maybe not to share too much content in just one window. Okay.
Okay.
Let me change the setting. Okay.
Okay.
Wait.
So how about
No.
I introduce this webinar again. I noticed that there is a slides actually send it to me. Maybe I can show that
Which slide?
The webinar introduction slide.
Okay. You mean restart the talk?
Actually, we can continue, but before we set up, actually we can show the slides of this session.
Okay. Oh, okay. Sure. So you mean you share the screen for the introduction?
Yes. Yes. Until you set up the configuration.
Oh, I see. Okay. No. Yeah, maybe we can you hear me? Hello, Tao, can you hear me?
Yes, I can hear you.
Okay. Maybe we just can continue because so we try to change the setting, but it doesn't work. So we just make this window smaller and yeah, just show the main part. Maybe we can try. How about we try it? Okay.
Okay, of course.
Okay, maybe we just continue.
Yes, sorry for the delay. Yeah.
Okay. I'm sorry. So so here we show some result. Okay. So we can see that the input is just a single wave video with different poses and expressions. So the second column shows the random result, which quite close to the input, and the final column is show the reconstructed surface. We can see that we can recover the whole head the whole head part, including the hair, for each frame. And based on this reconstruction result, we can use our laser input video to do this retargeting for this kind of reconstructed result. Okay, so we just introduced two works for this head reconstruction for static and dynamic. So we also extend this kind of method for closed human body reconstruction. So we also just based one single view video. Okay, so before design the algorithm, we need to first know what are expectation to human body reconstruction. So the first is that the capture hardware should be one single camera, such as a smartphone. In this way, every people can use his smartphone to do this capture. And the second that is the capture process should be easy. As shown in this example, the people just rotate before the smartphone, so the capture process is quite easy. And the final requirement is that the reconstruction result should be high fidelity. So this just show one example. So this is the algorithm pipeline. We the key idea is that we adopt this explicit and implicit geometry representation. So the reason why we utilize this both representation is that the mesh-based representation is very suitable for this kind of forward deformation. So as shown in here, so we do this kind of long-rigid deformation for this mesh representation, and non-rigid deformation plus this scaling-based deformation. So we formulate the whole non-rigid deformation. And but as we know that the mesh representation is has some limitations, like this kind of fixed topology, and it is not differentiable. So so based on this reason, we also adopt this implicit representation. And based on this implicit representation, we can utilize this inverse rendering. So currently there are a lot of work. So for example, this news or IDR, something kind of this method. We can use this photometric loss to back propagate this kind of information to update this SDF-based surface representation. So in this part, because this the capture process is dynamic, so we have this, we design this differentiable long-rigid recasting in this paper. So based on this kind of, we put all this together. We design this whole pipeline, and so we show some result. And okay, so the left shows the input single view video, and the right is show the corresponding surface reconstructed surface shape for each frame. We can see that we can recover the whole closed body, and especially for some challenge cases like this hair and this skirt. And we can see that we can reconstruct the result is quite good. And based on this, we this kind of design algorithm, we develop an application in App Store. It called linear scan, and you can download and try it. So it is this application is designed for this human body reconstruction. We also try this kind of design algorithms for some challenge cases. For example, we can say that okay, let me play the video. We can say that it's some good result can be obtained for this challenge case, because we can say that the people is just walk around and sit on the chair, and yeah, definitely it has some not good result for some part, but we can further improve the result, and we believe that it can be get better for these challenge cases. Okay. After we introduce this kind of surface reconstruction for the head and the body, we also consider also consider that if the final result is just for rendering, do we really need this surface mesh representation? So based on this consideration, we develop our algorithm called this kind of nerve blind shape for head part for head reconstruction. So we know that this mesh blind shape is quite popular for this face animation. For example, as shown in this video, so this is the input video. This is a recovered corresponding expressions, and its expression can be represented by this linear compilation of the predefined linear base blind shape. So we just for each frame we can just recover its corresponding coefficient. So okay, so if we just recover this this video, do we really need this mesh representation? Therefore, we develop our algorithm called this nerve blind shape. So the this is traditional mesh blind shape formatted in this way. For arbitrary expressions, it can be represented by a linear compilation of this kind of blind shape. So instead of combining bases in mesh representation, we generalize this concept of blind shape from mesh to linear radiance field. So we adopt a multi-level voxel field as blind shape basis, so which enables strong representation ability on the aspect of rendering and fast training. So this is the main idea. So in the left is a traditional mesh blind shape, and this part is the nerve-based blind shape, and we update or optimize the corresponding nerve-based blind shape based on this rendering loss to back propagate to get this corresponding nerve-based basis. Okay, so this is the input. It's also just a single view video. Okay, so this is a capture process. And this is a whole algorithm pipeline. So we first do this kind of face tracking. We get the corresponding coefficient, and we fix this coefficient and the coefficient is not optimized in the optimization process. So this is what we need to optimize this H1 to HK. This is it represents its corresponding nerve-based basis. We utilize this instant NGP, it means multi-resolution Hasse encoding to represent this nerve, and we use this kind of rendering loss to refine or update or optimize this corresponding basis. Okay, so this is a optimization process. So the input, this is the input video. This is the intermediate result of the optimization process. We can say that it takes around 20 minutes. We can recover all the corresponding nerve-based bases, and the final rounding result is quite close to the left one. Yeah, I also know that it also have some artifact. It's kind of like say, okay, here the tooth part is missing, but this year has a lot of following work to can get a much better result. Okay, so actually we also apply this kind of based on this idea, we apply this idea to some product. So the left is the input video, driving video, and the right one is the already recovered, offline recovered head model. So we can use this nerve blind shape using this drive video to do expression retargeting for the reconstructed nerve-based head model. We can say that so the input is just a single view video, and it is real time, and we can say that some micro expressions is also quite good. Okay, let's get faster. We also extend this nerve-based head dynamic head reconstruction for this dynamic human body reconstruction. So this is our recent paper published in TVCG. We call it intrinsic NGP. So we utilize this intrinsic coordinate for this hash encoding for human nerve. So the input is also a single video. It takes around 20 minutes, and then recover its corresponding closed human, and based on this recounted human recounted result, we can do this lower value synthesis and shape editing. So the first is that so it is based on this instant NGP. As we know, maybe last year, instant NG get attract a lot of attention from computer graphics and 3D vision because it's very fast for nerve training. It like takes 5 seconds for some for some scenes like this one. However, it is originally designed for static object or scenes. In their multi-resolution hash encoding, the input is absolute Aladdin coordinate. It's like here. So it is designed for static scenes. So we wanted to extend this this instant NGP from static to dynamic human body. What we think about is that although the human body is dynamic, but actually the coordinate is we can reformulate the coordinate from the absolute coordinate to relative coordinate. So what we did is utilize this simple model. So we recover simple model for each frame, and we do this 2D polymerization. So we get this UV coordinate for each surface because they will share the same message topology, and and so they share the same UV coordinate. And for each 3D dimension coordinate in the whole 3D space, we can compute its newest point on the sample model. For example, for this X, we can get its corresponding point P here, and P has this UV coordinate. So this is the UV coordinate for the X, and this distance we call D. So we convert this the original 3-dimension space to this UVD space, and we use this UVD coordinate for this hash encoding. In this way, although the human body has different poses, so the relative coordinate is keep as original as possible. Meanwhile, we know that this maybe this projection is not accurate enough, so we also further optimize this offset field. It's optimize this UV coordinate for each 3D coordinate for each 3D points here. So we have this offset field to further improve the corresponding UVD coordinate. Okay, let me show some example. We compare our method with this animatable nerve and human nerve. I guess so. This is this is the human nerve is should be from Hua-Seng University, and this is from Zhejiang University, and we can say that based on this based on our design, our method can converge very fast. It takes around maybe 10 minutes, can get a quite good result. Okay. So because we based on this sample model, so we can do some shape editing. We can just change the corresponding coefficient for the sample-based representation. Okay, we can make the neck stronger, or the body shorter or fat. Yeah, something like this. Okay, so after we do a lot of this kind of surface reconstruction, nerve-based reconstruction, so it's just for reconstruction. And for the real application, we need to do this kind of expression transfer or post-transfer or retargeting. And another popular application is this kind of, we just input some text or voice. We wanted to drive the reconstructed digital human. So this is just show one example.
大家好，我是央视新闻 AI 手语主播。从北京冬奥会开始，我将全年无为听障用户提供服务。手语主播，冬奥会开始。
So okay, from this example, we can say that so we can know that this digital human is not real, right? So it's so it's not real enough. Based on this, we have one work about AD nerve. So AD nerve is published in ICCV 2021. So the basic idea is very simple. So we just know the mapping from the voice to the talking head, based on this nerve representation. Because actually we do this kind of audio-based talking head maybe 2 or 3 years ago. It's so the first work we try to use this message-based representation like a 3D morphoboard or frame, and we just use this voice to drive the mesh, and then render the result. But we find that the result is not very good. After nerve is published, we think that it's a good chance to can get a better result based on this nerve representation. So the basic hardware is very simple. This is nerf, and we just add this kind of feature of this voice. We call it ETA, and the corresponding human pose, the head pose, this rotation and translation, and we do this. We learn this mapping from this this feature to the feather color and density. Okay, so let's show some result. So this is our digital human reconstructed this our nerf-based representation, and we just input some more text or voice. OK，
大家好，我是神会数字人平台生成的雪莉，很高兴认识你们。我可以做好多事情，可以唱歌。
When I was young, I'd listen
Spanish as well.
对话定在中街道。
こんにちは、私はシェリーシュです。これは私の日本語の声です。
Okay, so we can also use this method for this presentation. Okay, show in this video.
大家好，我是象眼实验室李东。首先，非常感谢大家来参加我的浙省自然科学基金委意识与重建和博士均。这个工作中用到每个体素的颜色和密度。
Okay, maybe we just need to conclude my talk. So, we can first we can reconstruct the high fidelity digital human based just one single video with this linear implicit representation and this inverse rendering framework, and for the future work we can further improve the capture convenience and the computation speed and the reconstruction quality. So, for example, robustness to the illumination, the human motion, and challenge expressions. And maybe currently the computation, the reconstruction speed is not very good because it also need to take maybe 20 minutes on the desktop. Maybe for the future work is how about directly computing reconstruction on the mobile device? And yeah, actually for this single video, the most challenging part is to fuse this motions or different expressions or poses, fuse them together to recover the motions and for the static the standard surface shape. So this is a very challenging case. So how can we combine or fuse different frames or with non-rigid deformations, non-rigid deformations together to recover this all this informations is also challenging. Okay. Yeah, thank you. That's my talk. Okay.
Okay, really appreciate Professor Ju Yong for the fantastic talk. Actually, I'm also doing research in the area of digital human, and I have read a lot of papers from Professor Ju Yong. And I have a little question. So okay. I noticed that you also made several products using based on implicit representations or nerves, and including an app on the App Store or many other production level systems. So I was wondering, so can you share a little bit about the biggest challenges for creating such a system for molecular digital human reconstruction for consumer usage?
Yeah, very good question. So actually, for this kind of product, maybe our the main product is this like kind of voice driving talking head. I think the most challenging part is that for the ordinary users, so they just use his smartphone to take a short video, and actually it's they don't care about the lighting condition. For example, in my current situation, the lighting is not very good, and so for many users, so they have very different challenge cases. So have various conditions. So we need to design our algorithm very robust to handle these challenge cases, some core cases. So this part is very challenging. So it's not. So for our research, we just maybe it works for some 10 examples. It's good enough. But for this product, you have a very challenging different conditions, and you need to handle most of these challenge cases.
Okay.
For example, for this kind of segmentation, and for relighting, and for maybe for some landmark detection. So you need to consider all of these cases.
Yeah. Actually, the whole pipeline is actually a little bit long, so any part could be erroneous. Yeah.
You mean which part is?
So any part have the opportunity to break. So you need to handle every model in the whole pipeline.
You mean which part of the whole pipeline can be handled?
I mean, for such a complex system, it contains many modules. For example, segmentation, detection,
yes,
reconstruction, animation, etc. So every part is very. We need to make sure every part is robust enough to make it very robust. Yeah.
Yes.
Yeah. Okay. So due to time limit, we don't have any other questions. So let's thank Professor Jiyong again for the fantastic talk, and we will also upload the video. I mean the fixed video on our website. So if you are interested in this talk, so remember to check our website later. So
okay. Thank you.
Thanks again. Yeah. Okay. So sorry for the delay. And let's start our second talk. Our second talk is from Shunsuke Saito from Meta. And the talk name is Digital Human Modeling with Light. So first, please allow me to introduce Shunsuke a little bit. Shunsuke is a research scientist at Meta Reality Labs Research in Pittsburgh. He obtained his PhD degree at the USC. Prior to USC, he was a visiting researcher at the University of Pennsylvania in 2014. His research lies in the intersection of computer graphics, computer vision, and machine learning, especially centered around digital human, 3D reconstruction, and performance capture. His work has published in SIGGRAPH, SIGGRAPH Asia, NIPS, ECCV, ICCV, and CVPR, two of which have been nominated for CVPR Best Paper Award at 2019 and 2021. His real-time volumetric teleportation work also won Best in Show Award in SIGGRAPH 2020 Real-Time Live. If I'm remember is correct, the name of the demo is Monopod. It's a very impressive demo. Okay, let's welcome Shunsuke for his talk.
Right. Do you hear me well?
Yes, very well.
And you see my screen, right?
Yes, we can see your screen. Yeah.
Awesome. Thanks for the introduction. It's a great honor to give a talk in this seminar. So today I'm going to talk about digital human modeling with light. Primarily centered at relighting, but I have some another thing to show as well. All right, so let's get started. So our Pittsburgh lab has been working on photorealistic avatars called the codec avatars. Our goal is to create an authentic avatar that's indistinguishable from reality. It should move like us, look like us, and sound like us. And this is our latest demonstration shown in our Meta Connect 2022. Here, two persons are talking in real time through their volumetric avatars. And their avatars are relatable, so they can control their expression, but not only that, but they can also change their illumination condition. So person hold their controller to move their light around, and then the other person can see that in real time. So with that, basically, I want to first motivate why relighting is so important in this metaverse or telepresence. So here's a kind of side-by-side comparison with and without relighting. So if you put a person without considering the illumination, then this composition looks highly unnatural. And if you look at the right side, with the relighting, the person looks like the person is actually in this space, right? So so relighting definitely improves the immersiveness of avatars. So in this talk, I'm gonna first talk a bit about the capture system and the data, how we actually get this type of data. So our capture system is called MAGSI. So it's a multi-view capture system, and it consists of 160 cameras, 450 lights. And for non-relightable codec avatars, we just turn on all lights. And this MAGSI allows us to capture a subject from many different angles, like you see on the left, with a various facial expression shown on the left. Okay. And what's more, this capture system is similar to light stage. I'm not sure in the video stream you can see it clearly, but we have a control of individual lights, and it's fully synced with the cameras. So by controlling those light patterns, we can collect different illumination conditions for each person. And let me first explain what we want to capture to actually enable relighting. So our multi-view capture system can observe the point X here from different viewpoints, as you can see here. And I plotted the observation point on the left. And if you also want to make it relightable, we also want to observe the point X under different light with a different light direction. So with this light direction, we want to see it from all the viewpoints and change the light, and we want to see it again from different viewpoints and so on. And this way, we can basically create a light transport matrix. Given the combination of light direction and viewpoint, we can reproduce how the person look in this particular viewpoint and the light direction. However, for avatars, this is not enough, because humans are dynamic. We actually move and speak and change poses, right? So that means this light transport is not only matrix, but actually a 3D tensor that also have a state. Because here state means expression or a human poses. By changing the state, also the light transport tensor matrix will change. Okay. And so from now, I'm gonna constantly use this a contrast between ideal and the reality. Usually, first, let's start what we want to get ideally and what actually get in reality. So ideally, this capture system provides this complete tensor. This way, we have there's no job on top of it. We can just rewrite avatar from any expression. But in reality, what capture system gives us is just a bunch of holes in it. So it only gives us a partial observation over a combination of light, illumination, and light expression and viewpoints. Because the capture system has a limited number of cameras and limited number of lights, and also it's infeasible to collect infinite variation of expression with a limited storage and also time. Okay, so and what we get is this time multiplex illumination. So over the course of time, we can change the illumination. So for each expression, we can turn different lights on and then like move on to different expression. That way we can correct all the variations. However, this requires the expression for each light condition. So it's left for our capture system with a 460 lights, it's roughly 460 times more capture time. This is apparently infeasible to do. So our solution is, given this limited observation bunch of holes in this light transport tensor, we basically learn like a function through a neural network, and let the inductive bias fill in all the intermediate observations. So let me first talk about how we actually overcome this the cost of dimensionality. Okay, so one thing we propose here is a time multiplex dynamic capture. So instead of asking people to be static for each expression, we let just our person to have a arbitrary expression in time. So this way, so for every frame, we can change illumination and also expression at the same time. And this way, as you can see on the left side, we see more observation across different light condition and expression. So this basically increases the chance of getting the better observation of light and expression pair, but it's also still limited. And what we did in addition is to turn on multiple lights at the same time, not only one light, but 5 lights, for example. This way, for each time, we have an observation of expression and the multiple lights at the same time. In a traditional work, like decoupling all the light sources is challenging, but by combining it with a learning-based approach like a neural network, we can actually also decompose the contribution of multiple light sources. I will talk about how we do this later. So this way, we can get basically 5 more lighting data for the same duration. All right. And another thing is a tracking, like how we get this state. So I mentioned that the state means expression, gaze direction, pose, and so on. And for the problem is, so our codec avatar system takes a multi-view capture system and run a 3D reconstruction, key points, and get the mesh tracking. That way we can build a high quality facial avatar called a codec avatar. However, in the relighting capture, as you can see, if you have only small lights on, then the part of the face is completely dark. It's really difficult to apply a traditional tracking with this kind of lighting frames. So our solution is to interleave free lit together with these partially lit frames. So here you can see that every 3 frames, we insert free lit, and then also we turn the other 5 lights from the random direction for the intermediate frames. So this is how it looks. So as you can see on the left, every 3 frames is used for tracking because it's free lights on. And for the remaining 2 frames, we use it for learning a relightable avatar. So this is a kind of sequence, like every 3 frames, you see that there's always the full lights on, so we can reliably learn a tracking algorithm, and then we can learn interpolation to get their alignment for the relighting frames. All right, so that's the data on the capture system side. So let's talk a bit about the algorithm side. So our original codec avatar is presented in SIGGRAPH 2018. The idea is to basically auto-encode the human's facial expression through an expression code and viewpoint with the variational autoencoder. As an intermediate representation, network spits out the geometry and texture, which is view dependent. And by combining them, you can render from arbitrary viewpoint with the different expressions. But this avatar is not relightable. So the naive extension of the relightable avatar is, hey, together with the viewpoint and expression code, what if we just condition the extra lighting information or lighting code? So the lighting representation here, just for the efficiency, instead of taking this high resolution environment map, we just downsample to 32/16. Okay. And for the training time, as I mentioned, we have 5 lights on, right? So we can take this type of 5 lights on as a lighting code, and then let the network learn how their appearance look from all those 5 light combination. And then in the inference time, we basically replace that with the environment map, which we want to render the avatar with. And then we can hopefully relight the avatar under arbitrary illuminations. And ideally, given this limited observation, we can basically create this function to produce a photorealistic avatar and the different illumination, different viewpoints, and expression. And however, what happens is the generalization is a problem. If you have a limited observation, like if you don't pick a right inductive bias, network does not generalize well. Let me briefly talk about that. So the RE condition model, as I mentioned, like taking just all lights in a lat long image, this is difficult to generalize to Nobel light distance, because here we assume that the lights are like infinitely far and all light directions are same. But in reality, our capture system has a distance to the avatar, and also like if you put the lights close to face, the light direction varies depending on the location of face. So what we propose is called the light condition model. So instead of taking the light as a RE layer as the input of RE layer of the network, we insert the lighting direction as a later part of the network, so that it's spatially varying, so that it can account for more local change of light direction. And this is what we get. And this allows us to render avatars from arbitrary light conditions, such as this directional light to actually a near field light. As I mentioned, our capture system is like a dome, which actually has a 1 meter radius. But we can, in the test time, we can put the light much closer to face and still turn the avatar relightable with a realistic appearance, as you can see on the right side. And here's another problem. So there's a huge domain gap between the training data and the test environment map. As you can see on the top, the light stage data give us these 5 lights on type of data. But in the test time, we want to basically relight the avatar with a more continuous illumination. And what you see here is if you just only train with this 5 lights on, the avatar does not generalize to produce realistic appearance under Nobel illumination. So our solution is to leverage the linearity of light transport. Let me explain why it is. So we can decompose the target illumination as a combination of multiple point light sources, right? And if you have an observation of a person's face or anything under each point light sources, since lights are linear, meaning if you have a light one from one direction and there's another light from the other direction, the contribution of 2 lights are linear, so you can just simply add them up. So if you basically take a weighted average of a multiple observation, you can actually produce a Nobel illumination condition. This is called the linearity of light transport. If you change the illumination, so you can, although you only have an observation from just a single point light sources, you can still turn those faces under different illuminations. And this is another extreme cases. Okay. And in our case, this all that observation is parameterized by neural network. So we take our light conditioned model to basically take this point light source and then turn this into a photorealistic appearance. And we can basically take a weighted average of those. We can turn the avatar into our Nobel illuminations. So this allows us to generalize to natural illumination, although we only capture with those light stage point light capture systems. Okay. There's another thing. So the speed is another important consideration for the digital human applications, because ideally we want to see the avatar in real time so that we can use it for communications. In an ideal world, this neural network based relighting model is fast enough that we can render in real time. So that, for example, as a state, we can take from a headset images and then relight avatar based on the facial expression in real time through VR. However, this like if you take a linearity of light transport and then produce a Nobel illumination condition, it's actually too slow, because for each light condition, we have to run a neural network and we have to add them up. So simply, if you have a like 16 by 32 environment map, this means we have to run a neural network 512 times. This is far from real time. So our solution is to use a student-teacher framework. So let me explain what that is. So as I mentioned, the array condition model is faster render because you can take whole environment map as an input. However, it needs a ground truth. Like as I shown earlier, if you only take those 5 lights on, it never generalizes. On the other hand, the light condition model gives us the good generalization. It can render faces under any illumination. However, it's very slow. So what if we just take a light condition model to produce a bunch of pseudo ground truths, and then training this early condition model so that we can render the natural illumination in real time? And this is called the student-teacher framework. So this allows us to render like faces in a more or less same quality with much faster rendering speed. But here on the left, you can see that our teacher model can produce natural realistic relighting results, but it's far from real time. And on the right, this is our distillated student model. With a more or less same quality, we can achieve 100 FPS. This is fast enough to render avatar through a VR headset. So from the camera stream from the head-mounted display, we can drive like our relightable avatar in real time, and we can preview it. Probably from online streaming, the video is a bit laggy, but hopefully you can see reasonable animation results here. Okay. All right, so we also extended the aforementioned pipeline to volumetric avatars. So these are the results shown here. We basically combined our volumetric avatar called mixture of volumetric primitive, which was presented in AsiaGraph 21, with our relighting algorithm. So this way, not only just a mesh-based avatar, but the volumetric avatar can be relit in real time with arbitrary illuminations. So here, in the middle, we show that we can put the light close to produce this near field lighting effect, but also we can turn the, like a volumetric avatar relightable in a natural illuminations, like you see on the right. So the quality of hair is significantly improved with a volumetric approach, like NAF or like our own MVP. And note that MVP is highly efficient compared to NAF, and we can also render in real time. Right. So sounds like we solved everything, but it's actually not the case. So there's still a lot of things to be done. So let me also talk a bit about how we actually create a more complete avatars with relighting. So there are a couple of limitations or the future work. One is articulation. So for body or hand, actually like humans are articulated. So we can change different poses, and still we want to relight avatar in real time with like a good generalization. The articulation poses extra challenges. Another thing is the composability. So if you have an avatar with accessory or like changing hair, but still like we don't want to lose the ability of relighting, right? This composition turns out to be non-trivial, and then we also propose a solution. So first, let's talk about the articulation. This work is like, so we worked on hand relighting in 2023, like it was published in CVPR 2023. So first, let me explain what are the challenges for relighting hand. The one issue is articulation, as I mentioned earlier. So if you change poses, then the shadow casted on the hand will change drastically. So there's an almost infinite combination of pose and illumination. First, observing all of them is difficult. Second, like generalizing to all those combinations is difficult. So this is something we have to address. And another thing is interaction. So ultimately, like we don't want to only use a single hand for anything. We will interact with the object or the two hand. And this type of interaction is very common in a real world scenario, right? And we still want to relight hand under this type of interaction station. This also like casts a shadow on the other hand and so on. To achieve the good generalization, in our work, we propose a so-called neural relighting with a physically based lighting features. I will explain it a bit later. So first, let me explain what our data looks like. So as I mentioned, we use the interleaving time multiplex capture. So similar to face, every 3 frames, we have all lights on. And for other 2 frames, we use the partially lit lights on. And then we use those remaining 2 frames for like learning a relightable appearance. And for this pre-lit frame, we use to learn the base geometry and the tracking. And here's our teacher model. So like we take local right direction, local view direction, and the shadow feature. For this taking shadow feature is really critical. On top of it, we want to create a pose-dependent effect such as wrinkle properly. That's why we also inject the pose information in the middle of the network. And this way, we can turn this shadow input, light direction, and so on into a photorealistic appearance of a human hand. And here's our results, the aberration study with and without shadow feature. And here, I'm going to flip between real data and our random model. So as you can see, the without shadow feature, it does not generalize to novel combination of light direction and the poses. And without shadow feature, the network can still produce a photorealistic shadow under novel combination of novel condition of illumination and the hand poses. And what's more, even for like completely unseen light trajectories, our approach can successfully model realistic shading. And note that the important bit here is since we go through neural network to produce final appearance, the input shadow feature, for example, doesn't account for subsurface scattering and the more complex global light transport effect. But by combining this local light feature and neural network, we can still produce photorealistic appearance incorporating all the global light transport effect. And we can also render hand under a near field illumination, although we capture hand from like a 1 meter radius dome. So we can also change the light, not only direction, but also the distance. So still there remains a problem. We want to support environment map relighting in real time. So as I mentioned earlier, for face, we also apply the same idea of student-teacher, teacher-student framework. The OLAT model, just as a quick recap, OLAT or teacher model can generalize the novel illuminations by leveraging this linearity of light transport. Since we have to learn this the network multiple times to aggregate the contribution from different light sources, it's extremely slow. On the other hand, our student model can generalize well, but our student model is a faster render, but it needs a ground truth data. So we pair them up and then just supervise a student model. For the student model, the big difference from the face work is we actually take a lighting feature instead of just simply taking the environment map as a long, like a vector. So here, similar to some of the portrait relighting work, like total relighting, we compute the diffuse feature as well as the specular feature, given the coarse hand proxy. And here, the important thing is for hand, we incorporate the visibility. So without incorporating visibility, it does not account for the correct shadowing effect, especially if you have multiple hands. So here's our results. Our student model can render hand in a reasonable speed. So this is a volumetric primitive-based hand model, and roughly the speed is 33 frames per second. it's reasonably real time, and we can render hand and the natural illuminations together with correct shadowing effect. As you can see, when the light moves, there's a shadow moving around on the palm. So here's an ablation study and the comparison. Here on the left, I show our results, and in the middle, our result without visibility incorporation, and the rightmost is basically the adaptation of our area work of face as it is. So without taking this spatially varying light feature, no visibility and so on. So as you can see, without visibility condition, the network does not produce correct shadow and sometimes produce artifact. And also like just naive extension of our face work does not generalize well. So this kind of will justify the way we kind of train this like relightable hand model, taking a spatially varying lighting feature for better generalization and the incorporation of visibility so that it can generalize to novel light direction and the pulse combinations. Okay. All right. So now we have a solution for articulation. So what about the composition? So in a digital world, we are not only just a minimally closed human, right? We want to put the clothing, accessory, and so on. But to support the relighting together with those accessories, we have to account for this composability. So let's talk about that. This work is called the Megane, Morphable Eyeglass and Avatar Network, done together with my intern, Junshan. So this work was presented in CBPL this year. By the way, this Megane literally means eyeglasses in Japanese, and that's why the abbreviation is Megane in this work. All right, so what are the challenges to learning this, to learn a compositional glasses, which is also relightable? So there are a couple of challenges. So you may think, oh, glasses share the exact same template, and we can easily just interpolate between those two. But actually, it's not the case. You can see that in the middle, there's some glasses that has two bridges. So actually, the glasses do not share the single topology. It can actually change the topology as well. And what's more, it actually consists of various materials. Some glasses made of metal, and also like others are made of translucent plastics. So it has a completely different reflectance property. And in the traditional approach, it's really difficult to represent glasses with a single representation. So for that, we basically propose to leverage a flexible representation. For shape, to support topology change, we leverage a volumetric representation like NARF. In particular, we use our like a mixture of volumetric primitives because it's fast to render. And for appearance, similar to hand and the face, we also leverage the neural relighting. So instead of using a physically based relighting approach, we use a neural relighting to account for subsurface scattering, high refraction, and all those complex light transport effect. Okay. And another challenge is actually the interaction between accessory or like glasses and the face. So they are not actually like deforming and changing appearance independently, but they are actually affecting each other. The first is a contact. So like there's a contact point between like a face and the glasses, and that causes deformation on both sides. Okay, and also there's a non-local shading effect. So here, as you can see, the glass casts shadow on the face. And this is also like a highly nonlinear and complex based on the different light direction. And also by changing the facial expression, the glass moves slightly. So this kind of motion makes it difficult to also learn a static shape of glasses. And for that, we argue that the joint modeling is necessary. So instead of modeling face and glasses separately, let's observe them together to learn those mutual like interaction effect. More specifically, so this is a naive version of this composition of glasses. Let's say we have a glass decoder that can span different type of glasses through this latent called ZG. And we have that for face as well. And this way, just, okay, if we know roughly where the glass is, we can just put them together in a 3D space, and then render. However, this is not, as I said, accounting for this mutual interaction effect. So that if the deformation is not correctly modeled, maybe glass actually goes inside the head, and also the shadow and those like global light transport effect is not incorporated in this relighting results. So what we propose here is the interaction decoder. This basically models this interaction effect for both deformation and appearance change. And we add this residual of deformation and appearance change to each decoder to produce a final appearance. For the data set, we correct, I think, 24 subjects with and without glasses. For every person, we ask to wear different glasses, like up to 2 or 3. And they are making different facial expression with and without glasses. And what's more, all the captures are this like the relightable capture. So we can change we can observe different light conditions for avatar as well. So here I show you the progress of how our glass geometry learns. As you can see, the glass shape and appearance emerge from the coarse initialization, which is just parameterize the plane to this through the volumetric inverse rendering. The leftmost is a ground truth image, and the second left is our rendering result after composition. As a result, we can build an interaction area generative model of glasses and heads. Now I interpolate latent code for face and the glass independently. So we can change glasses, but also identity. So here you can see that actually the model supported topology change. The glass changes the two bridge and the one bridge. This is not possible with a single mesh approach. So here I show the importance of our interaction area modeling. So let me show you the effect of our, the interaction layer. So here I flip between with and without our geometric interaction layer. As you can see, when the glass put on top of nodes, in reality, the nodes deforms, right? But if you don't account for this interaction, the glass goes inside the nodes. As you can see, without specifying what the deformation should be, our model automatically self-supervisory learn to produce this type of corrective through inverse rendering. So only the supervision signal here is the inverse rendering from images. Okay, so now we have a solution for geometry, and what about appearance? So we also introduced this interaction area neural relighting. Similar to our handwork, we also conditioned the appearance model with a shadow input. So this way, from this shadow input casted from the glass to the face, we can create a correct appearance effect, like a casting shadow with subsurface scattering effect on the face side. So here I show the aberration study of photometric interaction. I'm turning on and off this photometric interaction. This significantly improves the realism of a virtual try-on of glasses. To be clear, on the right, this is our synthetic image. The face and the glasses are all learned model, not the real images. And this basically leads to our free relightable computational glass and the face avatar models. The results shows that the single generative model can support photorealistic relighting of a diverse frame material of glasses with accurate non-local shading effects on the avatars. So here you can see that on the glasses, it correctly modeled the reflection, like specular highlight, and the subsurface scattering in the middle. In a traditional, physics-based approach, it's really difficult to model this type of complex, scattering effect in a single model, single generative model. All right, and there's another cool thing about our representation. So our glass model is partially volumetric, but it still retains this correspondence through the volumetric primitives. in a nutshell, it's basically representing volume as a composition of multiple small voxels. So that's why between different glasses, still it retains a correspondence. And what we can do is we can insert prescription lenses as an offline process. So we can semi-automatically detect where the lens should be, like as I show here on the red dot. And then, so we detect where the lens should be. And since the lens has a primary two effect, a reflection and a reflection, right? And given the shape of lenses, those effects are like uniquely determined. And what we do is when we shoot a ray, when we hit the glass surface, we just compute the two rays additionally for the refraction and the refraction, okay? So this way, even though we don't capture a subject with any like a precision lenses, we can still render avatar with a novel prescription. Here, as you can see, we can simulate like different near sight or far sight effect on the lenses. And here's our rendering results with a different also like a shading effect with the sunglasses. To be clear, none of those are real images, and the lens reflection is computed on the fly. All right, so let me briefly summarize what I have presented. So for the dynamic relighting capture, which is necessary for a digital human, we have to build and we have to develop a capture system and a data processing pipeline. The first key ingredient is a time multiplex group light. This allows us to address the cost of dimensionality, and with a limited reasonable time, we can still capture sufficient variation of combination of the pair of expression, right direction, and viewpoints. Also, to enable tracking, we propose to interleave free lit frames. And this way, we can run a tracking on a free lit, but still interpolate for the remaining frame to learn a reasonable relighting appearance model. So another key takeaway is how can we achieve generalization? My go-to is to use correct inductive bias. So there are a couple of like a physical phenomenon in this relighting. For example, there's a linearity of light transport. Then like one way is to explicitly introduce this linearity of light transport in the learning process. Also, like we show that the physically based features, so there's certain things we know about physics, like, okay, shadow should be casted from this direction, reflection goes this direction based on the surface normal. So these things can be pre-computed as a feature and they feed it into the neural network. This improves the generalization of the network, but also improves the fidelity. And what's more, like a compositionality is the key for the better generalization. We want to achieve basically like a good like a generalization for the novel combination of, say, accessories like different glasses and the faces. And for that, I argue that the representation need to be interaction aware, not only photorealistically, but also geometrically. This should account for the both deformation and the appearance change. Okay. So far, actually, this is not the end of my talk. So far, I've been talking about the digital human modeling with light, which is visible, like basically an RGB domain. What about the digital human modeling with invisible light? Let me explain what I mean by that. So for hair 3D reconstruction, and this is a really notorious and super challenging problem, because I think the core problem here is the hair interior is never observable from the visible RGB domain. You can see the surface of hair, but you never see the interior structure of hair. This is especially challenging for curly hair, like I show under the left bottom. So in this, so we present our work in a SIGGRAPH this year called CT2 hair. So our key idea is let's see through it. So how? How can we see inside of hair? Our solution is to leverage X-ray. So X-ray can pass through most of objects except metal, and actually we can see through inside the hair structure. More specifically, we leverage computing tomography and let us see through inside of hair. So here's the density volume we get for hair. For those the hair in data, which I show on the previous slide, basically I get this type of density volume. And it's very high quality, and it also has a correct interior information. You may think, okay, then the problem is solved. Actually, it's not really the case. Eventually, what we want is not only just a density volume, but a hair strand representation from top of from the root of the scalp to the tip of hair, right? This way, we can use a physically based like a rendering framework or physics-based simulation. Volumetric alone is not sufficient for this type of applications. So here's a problem. Like, it looks great, but if you zoom in, actually this density volume is very noisy. And this is kind of a fundamental limitation of a CT scanner. So the question is, how can we robustly build a hair strands from this noisy density volume? And in fact, if you apply a gobble filter, like classic orientation estimation, it becomes very noisy and difficult to rely on the prediction. And we basically propose a robust orientation estimation inspired by our a vector calculus, a tensor calculus. The key idea is always a hair a tangential direction, and the density volume gradient direction is orthogonal. And we solve this as an eigenvector eigenvalue decomposition problem. And this way, we can obtain much more accurate orientation information from this density volume. Comparing against the gobble filter, you can clearly see the improvement. And the left and right bottom, I show our reconstruction results versus gobble filter. This also leads to better reconstruction of hair strands. On top, we also propose a cost to fine optimization. So from this orientation assigned density volume, we specify it and then only extract the reliable hair strands and then do the filtering to only take the strands that comes from the root of scalp to the tip of hair. And then we do the interpolation and extra refinement process to get the final hair strand representation. So here I show you our final strand reconstruction result. As you can see, our approach can produce very realistic, plausible hair strands from a CT scan in a free automatic manner. There's no manual process involved, and it supports a wide range of hairstyles, which was not really possible with the prior approaches. So here I show you the comparison with the prior approaches. There are a couple of learning-based solutions, like neural HD hair or DeepMBS hair. And those definitely give us plausible hairs, but it's just plausible, not really accurate. If you zoom in, there are many local details missing and incorrect. And the second right image, we show that the comparison against a line-based multi-view stereo. This gives us a strand accurate reconstruction, but only for the visible area. It completely lacks the interior information. So, as you can see from the image-based solution, getting the accurate interior is very challenging. On the other hand, our approach can produce very realistic and accurate hair strands from the CT data. All right, so let me quickly summarize. So for the digital human modeling with light, not only we can make the avatar relatable, but also we can see something that was not possible in the RGB visible domain. For example, X-ray lets you see through, so you can account for the occlusion problem. And we also propose a robust orientation estimation with a vector calculus and a cost to fine optimization for robust reconstruction. And what's most important is we release code, model, and the data. So if you're interested in this super high quality CT data of hair and building even better reconstruction algorithm, please check out our code and data. All right, so that's all for my presentation. Thanks for listening.
Okay, fantastic talk with super strong visual effects, actually. Thanks, Shensky, for the very detailed explanation of both the inherent theory and also the design philosophy of creating digital human with light. I have a bunch of questions. So the first one is actually not everyone have the opportunity to get access to such advanced data. Actually, so do you think it is possible to use monocular camera? Actually, Professor Ju Yong, the first talk is talking about monocular camera-based human reconstruction. So do you think it is possible to use monocular camera with light or not to achieve also production level results if we can, for example, well utilize current advancement of AI, for example, diffusion models, foundation models, or something else? Yeah.
Yeah, it's a great question. So I think ultimately the answer is yes. But I think here, this like a kind of in the wild reconstruction, I also originally from this kind of background as well. I think requires good data player, as you mentioned. So this requires like good training data or the good observation. Like without knowing, like what the target is, it's really difficult to achieve this type of high quality results. That's why, like, so in my PhD, I'm more pushing from a limited input and then try to achieve the best quality as possible, like PyFetch and stuff. But here in the reality lab, I'm kind of approaching from the other direction. Given the highest quality data, what's the best quality we can achieve, and then how we can reduce the input. Like ultimately, what we want to achieve is from, as you said, from minimal input, we want to achieve the best quality.
Yeah,
I think like we have to kind of like merge them together. We have to first collect high quality data, high quality like algorithm, and then like produce a bunch of data to learn a data player. And this definitely help us learn or like regress a high quality output from in the wild data. So I think we are in the middle of this journey and we still don't have a working solution for that. But down the road, I think this is certainly possible.
Okay. Yeah, I totally agree with you. And my second question is, I'm very interested in the mechanism work. So my little question is for the glass generator. When collecting the data, you need people to wear different glasses and do different extractions. So I was wondering how to do you need to segment the glass from the head? And do you first reconstruction and then segmentation, or first segment the class in the image and then reconstruct the class independently?
Yeah, it's also a great question. So like we for this work in particular, we basically try to leverage the best possible segmentation. So like we indeed run our image-based segmentation on the glasses, and that's consolidated in the form of like non-rigid ICP. So like we basically first reconstruct a glass template for individual glasses, and then based on segmentation key points, those like annotation data we have, we basically try to first filter the glass geometry to easier the training process. But actually, there's a new ICCB paper this year I have, which is basically removing all those constraints. It's a bit different domain, but instead of taking this high quality segmentation and those annotation data, let's just have a two pair, with and without accessory. Can those like two set of just semantically separated capture is enough to separate the component? And then we found that the answer is yes. Well, we only did it for geometry. Like this is a collaboration with the Seoul National University, the Hanbyo, under his student Teksu. So if you are interested, please check it out. But as I said, for this work to achieve the best possible quality, we rely on this type of high quality annotation data. But down the road, I think all we need is like a semantically separated kind of a data. So like instead of just getting better annotation, but we can also add just extra label, like with and without accessory. In a natural, like in a semantic level, if you just subtract with accessory and without, you should be able to get just accessory alone, right? And together with like generative modeling, this seems to be feasible. So this is a very interesting and exciting direction, I believe.
Very interesting. I will definitely check this paper later. And my last question is, I noticed that you mentioned the MVP. It's very efficient volumetric representation for avatars. Recently there is also another work named Gaussian splitting. It's a little bit similar to the MVP. And can you? I was wondering. Have you ever tried to use Gaussian splitting to replace MVP, or in your opinion, the difference between these two methods?
So we did some experiment with Gaussian splitting, and I think short answer is like Gaussian splitting can be be a bit more efficient, like primarily because the Gaussian splitting relies on rasterization. Whereas MVP still relies on the ray marching. So for the ray marching, we first have to know, which voxel intersect and then aggregate around the ray. And rasterization is actually blazingly fast, and the couple of implementation difference, more or less they can achieve the same quality. And the one thing to note is Gaussian splitting seems to be is actually good at representing like a thin structure. In the original paper in Gaussian splitting, they showed that the spike of a bike tire was really well reconstructed, which is pretty difficult with other volumetric approaches. So there's kind of pros and cons, but generally there's some unique advantages of Gaussian splitting, and I think they should co-evolve. It doesn't necessarily mean MVP is not useful anymore. I think it still has its a use case, but I think that leveraging this type of more point-based representation in a generative modeling seems to be a very exciting and interesting direction.
Yeah, of course. Totally agree with you. So that's all for all of my questions. And due to time limit, we will end that here. So thanks, Shunsky, again for the fantastic talk. And thanks all the audience. And see you next time. Thank you. Bye.
Thank you.